Hi everyone. In today's video, we will be covering Chapter 6, which revolves around the concept of sampling and sampling distributions. Up until this point in the course, we have been primarily concerned with samples, and so to revisit these two terms briefly, the difference between a population and a sample is that a population encompasses the entire group of individuals or observations that we are interested in studying, so it needs to include every single member. Whereas a sample represents a subset of a population that we select to study them. A sample is oftentimes used to make inferences about a population because studying the entire population is oftentimes impractical or impossible even. So this is the point in the semester where we will be shifting from our descriptive statistics unit, so simply describing and organizing data, into inferential statistics, where we will be making inferences about our data and an entire population. A very common example of this is election polling and election data. The job of a pollster or a statistician that studies polling is to create what's called a representative sample. We had talked about in an earlier lecture how difficult it can be and how nearly impossible it is to survey every single member of a population, especially when it is so large, such as something as the population of an entire country. It's unreasonable to expect that a pollster would be able to get in touch with every single American in the United States. And so what their job is to create a representative sample of a certain voting block. And so oftentimes this is done at the state level, because state populations vary as well. What they do in that case is try and make it a representative match to what the population statistics look like as a whole. So let's say in Missouri, for example, that about half the population is men and half the population is women. And so the pollsters will want to make sure that they are sampling about an equal number of men versus women. They would also want to take a look at other demographic characteristics as well, such as race, socioeconomic class, age, things of that nature, to make sure that they're not oversampling one particular group. Because again, they're trying to make inferences using a smaller sample about how the entire state of Missouri might vote, just using that smaller number. And so that's something to keep in mind as we are moving through this next chapter, where we'll be talking about different sampling strategies that can be used to make those inferences from a smaller sample to a wider and larger population. Before we discuss all of the various sampling strategies that statisticians use, I want to make sure that we have a firm understanding of the difference between these two terms listed here, which is a parameter and statistics. Up until this point, we have been primarily concerned with this idea of statistics, which refers to numerical values that are calculated from a sample. These values are used to estimate and make inferences about the characteristics of a wider population. Statistics are also calculated using sample data. However, now that we are shifting our conversation from descriptive statistics to inferential statistics, I want to be mindful of this new term here, which is a parameter, which is a numerical value that describes a characteristic of an entire population. Importantly, parameters are fixed values, but oftentimes they're actually unknown because it's impractical for us to collect data from an entire population. A way that you can use this as a quick study reminder is that parameters deal with populations, so both are P's in that case, and statistics deal with samples. So again, we have the S's matching and the P's matching. Because we're using two distinct groups, there are actually different symbols that statisticians use to denote the difference between various forms of statistics listed here on our furthermost column in terms of whether we're using samples or populations. So we have sample statistics and population parameters. In this case, this first column should look familiar to us. These are the ones that we've used up until this point. We've used Y bar to designate the mean, a lowercase p to denote proportion, standard deviation, an S squared for variance, and a lowercase n for a sample size. However, we have a couple more symbols that we'll need to know moving forward and that you'll see me use throughout my slides or in your book, and those are our new population parameters. And so now, when discussing a population rather than a sample, our mean is going to be designated by this symbol right here, which is pronounced mu. Next, for proportions, we have the pi symbol. Standard deviation for a population parameter is now going to be represented by the sigma sign, whereas variance is represented by sigma squared. And now that we will be encapsulating an entire population, we are going to shift our sample size designee from a lowercase n to a uppercase n. So just something to keep in mind now that we're shifting our understanding of our chapter information from statistics in chapters 1 through 5 to population parameters now throughout the rest of this course. And so just know that that switch is occurring. Also that these statistics pretty much mean the same thing, but the designation is going to tell you whether or not we are talking about samples or populations. Oftentimes, we cannot test an entire population, which is why we have this idea of sampling in the first place. The most common of which is a probability sample or a random sample. Both of these techniques, those are interchangeable terms, is so that we can take a sample that is representative of an entire population. So this is an equal probability of selection method. In other words, every single individual within a population would have an equal chance of being selected. But let's first talk about this idea of probability in the first place. Probability is a measure of the likelihood that a particular event will occur. And we measure this on a scale between 0 and 1, where 0 indicates that an event will not occur, and 1 indicates that it will absolutely occur. It is a certain event. Probability helps us make predictions about the occurrence of events, and it's based on known data or assumptions. The formula that we will be using to calculate probabilities is listed here, which is simply in our numerator that we have the number of successes, and we divide that in our denominator by the number of possible outcomes. And so let's take a look at what that looks like with an example. Oftentimes, I like to discuss probability in terms of dice and cards. I think it's something that a lot of us have a level of familiarity with, and it's a good way for us to understand probability in a very simplistic manner. Notably, probability is written as P event. So if I ask you, what is the probability of rolling a 6 on a 6-faced dice? This is how I would designate that here. So again, what is the likelihood or probability in this case that I would roll a 6? And in order to calculate that probability, all I need to do is take a look at this formula here, which I borrowed from the last slide, which is looking at our numerator of number of successes. So again, if I have a 6-faced dice, it all has a different number on it ranging from 1 through 6. So each face has a 1, 2, 3, 4, 5, and 6. So my probability of success of rolling a 6 is a 1 in 6 chance, right? The number of success, I have a 1 in 6 chance, and I have 6 possible outcomes. If I divide that together, the actual probability here is listed as 0.167. And if I wanted to convert that into a percentage, I could do that pretty easily as well by either shifting our decimal point 2 spaces here or multiplying by 100. So the odds or percentage in this case of rolling a 6 is 16.7%. But what about if I took a standard deck of 52 cards? What is the probability of drawing just the 10 of hearts, so that one specific card? Well, again, I know that there's only one card in the entire 52 that is the 10 of hearts, so my probability of just pulling that is 1, right? There's not multiple of those cards within the deck of 52. But my number of possible outcomes is 52. So again, all I'm doing is my one chance of probability of actually selecting the 10 of hearts and dividing that by all of the possibilities in the deck, which is 52 cards, to get a probability of 0.019. Or if I wanted to convert that into a percentage, I have a 1.9% chance of selecting a 10 of hearts from a standard deck of 52 cards. So knowing that that is how we would calculate a probability for a single outcome, in this case rolling a 6 or selecting one specific card from a deck of 52, ask yourself this question here. If you need to go back and reference the probability formula on the last slide, feel free to rewind the video or go take a look in your notes for that. But what is the probability of drawing a heart out of a deck of cards? As a reminder, there are 4 suits within a standard deck of cards. We have hearts, diamonds, clubs, and spades. And because of that, each one has 13 options. So keep that in mind. Go ahead and try and figure this out on your own, and on the next slide, I will reveal the answer. So go ahead and either pause this video or just give yourself a moment to think this through. Okay, the probability of drawing a heart. Again, I am representing this as P event. So the probability of drawing a heart, we will figure out via the number of successes divided by the number of possible outcomes. And in this case, as I had mentioned on the previous slide, there are 4 different suits in a standard deck of cards. So each one has 13 options here. So that is my probable number of successes, right? There are 13 cards in a standard deck that are hearts. Out of 52, which is all of the possibility of cards that I draw, I have a probability of 0.25 of drawing a heart from a standard deck of cards, or in other words, I have a 25% chance. Let's talk about probability, though, in terms of criminal justice. So again, I use the idea of dice and standard decks of cards to illustrate what probability actually is. We use that a lot when it comes to talking about the fundamentals of probability, but how would we actually make this applicable to our studies of crime and criminal justice? Oftentimes we see probabilities expressed as percentages, which is what you saw me convert some of those findings that we have in the last 2 slides to. Reason being is oftentimes percentages are a little easier for us to understand and interpret, and so frankly that's why we use them. What this graph is showing us here is the lifetime chance, or another way that we could have phrased it is the lifetime probability of being sent to prison at current U.S. incarceration rates. This study comes from the Prison Policy Initiative. And what it's showing here is all different groups. So we're able to understand disparities within our criminal justice system. And so if we were to look at all Americans in the entire United States, so population level of our country, you have a 6% chance of being sent to prison or being incarcerated at some point during your lifetime. If we were to only look at the population of men, that increases to an 11% chance. Now we can disaggregate this by not only gender, but race as well. We see a 17% chance for Hispanic men of being sent to prison and a 32% chance of African American men. And so that's something that we can use probabilities and percentages to be able to communicate to a reader of not only how incarceration affects all Americans, but also specific subgroups as well. To advance our conversation on probability sampling, I want to go into 4 different techniques in further detail. The first one is a simple random sample. The second is a systematic random sample. The third is a stratified random sample. And the last one we'll go over is a cluster sample. The first type of probability sampling technique that we will discuss is a simple random sample. And a simple random sample is a system of selecting a sample where all cases in the population have an equal probability of being selected. And that is our key term here, equal and equal probability. There are a couple key characteristics of simple random samples that I want to bring your attention to. And the first aspect of that is this very concept of equal probability. So again, really driving this aspect home. Equal probability, again, is just that every individual in the population has an equal probability of being chosen. So no one has a greater chance than another person. The second characteristic is independence, or that the selection of one individual does not influence the selection of another person. And lastly, random selection, in which the process of selection is entirely random. And oftentimes we use techniques such as a random number generator or other types of randomizing techniques to ensure that it is truly random. Unlike a simple random sample, a systematic random sample is a probability sampling method where elements are selected from an ordered population using a fixed interval. So let's break this down a little bit more. The key characteristics of a systematic random sample is that first aspect that we just mentioned of this idea of a fixed interval. So what does that mean? After a random starting point is determined, every certain observation has a chance of being selected, but it's done in a systematic way. The second element is order, meaning that the population must be ordered in some way before sampling even begins. And the last element is a random start, meaning that the starting point is randomly chosen within the first interval. So let's say in a criminological sense, I was interested as a researcher in measuring the perceptions of public safety within a certain neighborhood. But as we know, neighborhoods are quite large, and so it's not always possible for me to interview every single individual within a certain neighborhood. But to ensure that I have a representative sample of what the population is as a whole in that neighborhood, let's say that I was on a block of 100 different houses. I know that's quite large, but 100's a round number, so we're going to go for it for now. And within that 100 block house neighborhood, I want to do it in terms of fixed intervals of every 10th house, right? I don't have the manpower to go to each individual door and knock on it and say, hey, what are your perceptions of public safety in your neighborhood? How safe do you feel during the day versus the nighttime? So on and so forth. But if I do every 10th house, that can cut it down quite a bit. And it's still a random start. I didn't pre-select a certain house to start with before I got there. And it's every 10th. Oftentimes, we don't see this used in social science. I would see a simple random sample or some of the other techniques we're going to get to in just a moment. Know that this one exists, and the reason is it's really a manpower issue, right? How quickly could we survey a group instead of 100 houses to kind of narrow in on the resources that we do have? But there are other techniques that I would argue give us a little bit more of a representative sample and can be more helpful in the social science realm, but just know that this is an option for you if you want to seek it out. The third type of sampling technique that we will discuss is a stratified random sample. And this is a probability sampling method in which a population is divided into distinct subgroups, which are also referred to as strata, that share similar characteristics. There are a couple key characteristics of stratified random samples, and the first is this idea of the division into strata. And so let's take a step back here, because I'm pretty sure this is a new term for a lot of you. And in this case, the strata refer to the population being divided into non-overlapping subgroups, and it's based on a certain characteristic. Oftentimes, we do this as social science researchers in terms of demographics of our sample, whether it's something like age, gender, race, or income level. And the reason we do that is so that each of our different strata have proportional representation. So I'm actually going to jump to this third bullet point here. And so what this is alluding to is this idea that the sample size from each stratum is proportional to the size of the stratum in the population. But it can also be equal for each stratum depending on the study design. And so what does that mean? That's a lot of information. Again, thinking back to this idea of our demographic characteristics, and I'll bring this back to an idea of polling for presidential elections. Let's say that we had a pollster come to St. Louis and they were interested to see what St. Louisans were thinking about two presidential candidates. If they randomly sampled, right? That's the first one we have, a simple random sample. Everyone has the same opportunity of being selected. But that simple random sample ended up with a sample of 80% men and only 20% women. We know that isn't exactly representative of what the population of St. Louis is, right? It's about a 50-50 split. So that's one of the disadvantages of a simple random sample is even though everyone has an equal chance, we know that people oftentimes have different political views based on demographic characteristics such as their age, socioeconomic status, and gender, and things of that nature. And so it's important for us to be able to divide these people into strata accordingly and sample from them to make sure that we're truly getting that representative sample. And then I'll jump back to the second bullet point here, which is the idea of random sampling within the strata themselves. So once we establish what those subgroups are, so in this case, let's go back to the idea of men versus women in terms of our presidential polling. Once we divide those strata into equal groups, right? Division into strata, about that 50-50 split, we're going to randomly select within those strata itself. So once I divide our citizenry population of St. Louis into men and women, each woman would have the opportunity to have an equal chance of selection, and each man would have an equal chance of selection as well. And so in that case, what you're preventing doing, let's say those pollsters wanted to have a sample of 1,000 people. And again, that simple random sample example I gave you is that 80% could be men, which is 800 versus only 200 women. What they're doing by creating those strata or subgroups is ensuring that they essentially interview 500 men and 500 women. But then when they establish those two subgroups, they're able to randomly sample within that. But it's to ensure that it's a more overall representative sample than something like a simple random sample or even a systematic sample. But again, this could be applicable to certain types of research questions more than others. I think as social scientists, it's oftentimes utilized for us because we're interested in different social phenomenon that do have differences across different identities such as socioeconomic status, age, race, gender, things like that. And so we use this one quite a bit when it comes to probability sampling. The final probability sampling method that we will discuss is cluster sampling. And cluster sampling is a probability sampling method where the population is divided into distinct groups, which are also referred to as clusters. These are usually based on geographical or administrative boundaries. So instead of sampling individuals directly, as we might within a simple random sample or even a systematic random sample, entire clusters are randomly selected, and then either all individuals within the chosen cluster are included in the sample. That's referred to as one-stage cluster sampling, or a random sample of individuals within those clusters is taken, which is known as two-stage cluster sampling. Let's talk about each of these key characteristics below in a little bit more detail. The first is this idea of clustering itself, and this is unique and different from what we talked about in the last slide about strata. So whereas strata is something we can manipulate as researchers, in that case with the previous example, we wanted to ensure that half of our sample represented the male population and half represented the female population. Clusters are naturally occurring. There are things like schools or neighborhoods or districts. Within each of those clusters, we have the random selection of those clusters themselves. So once you determine what your area of interest is, let's say it's schools within a district, each of those schools would have an equal chance of being selected. So that's where our random selection aspect comes in. And lastly, this key characteristic of sampling within clusters is only really relevant to this two-stage process at the end. So if you engage in two-stage cluster sampling, not only are you selecting the initial cluster itself, but then within that cluster, you are randomly selecting and choosing individuals to participate as well. Let's take a moment and step back and provide an example of what cluster sampling might look like in practice. I think that'll give us a lot better of an idea of how this actually works. So let's say that I was a district administrator for a school district. So I'm in charge of, let's say, 10 different schools. And I want to know how safe my students feel getting to school every day, whether they're walking, taking the bus, or maybe they're being driven or driving themselves. And because of that, I know I want to interview a lot of these students, but I don't necessarily have the capability to go to every school and interview all the students, because you might be dealing with hundreds, if not thousands in that case. And that's not really realistic for us to get an overall picture and understanding of how safe our students are feeling getting to school. In this case, what I could do is a cluster sampling technique in order to kind of dwindle down our options here. So I might select a single school to serve as my cluster. Importantly, each of those 10 schools within my district would have an equal random chance of being selected. And so I'm not sure which one I would choose. I could use something like a random number generator or another random sampling technique to figure out which of the 10 is going to serve as my cluster. But once one is chosen, that could serve as my actual ground for surveying my students. If I were to engage in a one-stage cluster sampling, that would mean that once I select my cluster, or my one out of the 10 schools in my district, I would then have to interview all individuals within that chosen cluster, or the entire school. But let's say that that school I selected has 500 students in it. That's still a lot of students to survey. And so maybe I choose to do a 2-stage cluster sampling technique instead. And what that would mean for me as a researcher or someone trying to conduct a survey is that within that cluster school I selected, there's 500 students. I could then take a random sample of those 500 students, so that's that second stage, to see what their perceptions of safety is going to school. So maybe I dwindle it down from the 500 students at the entire school to maybe only 100 of them. And so that's a lot more realistic for me to be able to complete as a researcher and an administrator. But because I was engaging in these random sampling techniques the whole way through, hopefully that subsample is a representation of what the views of are all of the students in our district as a whole. Let's briefly compare all of the 4 probability sampling techniques that we've covered thus far. So first, simple random sampling is our most basic and rudimentary form of sampling, right? It's where every single person has an equal and random chance of being selected. There's no manipulation that we are doing on our end as researchers in the selection process itself. The second is a systematic random sample. I use the example of neighborhood research in which every 10th house was selected from a block. So again, there's still the random start, meaning that I didn't pre-select which house I was going to start with, but then every 10th house would be selected from there on out. Stratified sampling is oftentimes what we use in polling research and is used by statisticians to ensure that they have a representative demographic sample of a population, whether that's at the local, state, or national level. And lastly, with cluster sampling, oftentimes we use this when we have naturally occurring clusters in and of themselves. We just discussed what this may look like in terms of perceptions of safety of getting to school every day, and how we could use this sampling technique within a district to still interview our students, but in a way that uses a lot less resources. So although we can use each of the 4 different types of sampling techniques to try and ensure that we get a sample that is representative of a population, this type of technique does not necessarily guarantee a representative sample. So although we can try our best, that doesn't mean that we will always get one. However, the probability is very high that the sample will be representative. Inferential statistics allows us to estimate the probability of the type of error in which we may not get a random sample. Once we use the various sampling techniques that we've discussed this far to establish a random sample, how do we go from our established sample back up to make conclusions or different observations about the population as a whole? Well, we do this through what's called a sampling distribution, which is the distribution of a statistic. We commonly use means, but sometimes we use things such as proportions or standard deviations for all possible sample outcomes. And let's take a look at an example of what do I mean by this. How do we go from our individual sample back up to a population? In this case, let's take this example here of the average amount of time we spend on social media in the population. So we're going to specifically focus right here on the year 2018. You can imagine if this line graph was extended even further, I would have to imagine that the amount of time would probably exponentially increase at this point, as we've had the addition of a lot more social media platforms and the availability of smartphones. But again, just using this particular graphic, the average amount of time spent on social media per day in 2018 was 2 hours and 22 minutes, or in other words, 144 minutes a day. And so we're going to use this example, which uses the average or the mean, to illustrate how we can go from our sample to the broader population. So using that example, we can essentially take a sample and calculate its mean over and over and over again. And eventually what happens is the creation of this bell-shaped curve, which is getting us back to our discussion about the normal distribution. So we can plot a distribution of our sample in mean times, which are all these different y bars. Remember that y bar stands for mean of a sample. The reason that we use mu, though, is because we're trying, again, mu is this little U-shaped thing here, for the entire population, but each individual sample mean is represented by this y bar. So, if we were to keep taking samples and plotting these means over and over and over again, because keep in mind, sometimes with our samples, if we were to take a look at our entire population of the United States, there might be some samples in which people are spending far less time on social media, right? Maybe somewhere in this region of only about an hour a day or 60 minutes. But our average time in the population was that 144 minutes. But we could have another sample in which perhaps those individuals were spending a lot of time on social media, upwards of 4 hours per day, and they might have that average here with Y bar. But eventually what we would have created is this bell-shaped curve with all of the different averages that are stacked up on one another. So another way to visualize this, again, is our mu, or our population average, our mean, is a value of 142 minutes, or that 2 hours and 22 minutes per day on social media. I've already done this for us, but using that information, you can also calculate sigma, or what our population standard deviation is, which in this case is 20 minutes. Also importantly, and this will go into our next slide as well, is this idea of sample size. So remember, using a capital N designates the overall sample size for a population. Within statistics, we always want to make sure that we are using a sample size of over 30. Why? That's just kind of what's been established in the statistical literature. I honestly don't have a good explanation for you on that one. But just keep in mind that it is 30. That's our cutoff point. Ideally, for this example with the social media, we would want to take something like at least 100 samples at a time to get something that more resembles that bell-shaped curve. I alluded to this on the last slide, but this idea of getting eventually towards that bell-shaped curve is summarized in this idea of the central limit theorem. It's also referred to sometimes in your book, or if you look this up online, as the CLT. What this theorem proposes is that for repeated random sampling with a large sample size, so anything greater than 30, once we do that, the sampling distribution of the sample means will result in that normal distribution, or again, that bell-shaped curve. The mean of the sampling distribution will be equal to the population mean. So in that case, we would have mu, which is our population mean, be equal to our sampling distribution mean. The standard deviation, which is also known as the standard error of the mean, will also be equal to the population standard deviation divided by the square root of the sample size. And we'll get into that in a little bit, but this is just that overall theoretical orientation here. What does this mean in terms of math speak? Well, if all possible random samples of size n, so again, we're using our entire population here, are drawn from any population with mean mu, again, our average of the population, in the standard deviation of the population, sigma, as n becomes larger, the sampling distribution becomes approximately normal, again, that bell-shaped curve, with mean mu in the standard deviation formula designated by this, and we'll get to this calculation in just a moment. The central limit theorem applies regardless of the distribution of the variable, and so regardless of what your sampling distribution ends up being, it could be any of these odd shapes, right? We see what happens when our sample sizes are small. Our distributions look very wonky in nature, right? Eventually, though, what it proposes is the more and more samples we take, the more so we will resemble that bell-shaped curve. In terms of the standard deviation of the sampling distribution, this is now referred to as the standard error of the mean. It gets smaller as n becomes larger because we are more so resembling what that true population distribution is, or that bell-shaped curve. Let's take a look at these two examples here on the right, because I think it'll help us illustrate this a little bit better. Let's take an example of a simulated sampling distribution of sample means only using 5 different samples. You can see here that some of those samples might be clustered together, right? We're only looking at 5 here total, where if we increase our sample size of our sampling distribution to 30, we start to resemble more of this bell-shaped curve that is our normal distribution, in which we know that the mean, median, and mode values are all at that center point. And that's where we can establish our mu, or our population mean or average. As we reach the conclusion of this chapter video, I know this was probably a lot of new information for folks, so I really want to point your attention here to this final summary slide. This is the first chapter in which we have shifted our conversation from samples to populations. And because of that, that changed a lot of the language that we had gotten used to through chapters 1 through 5. So if you need to watch this video again, I highly encourage you to do so because it will set you up for success in both chapters 7, 8, 9, and 10. With that being said, first, make sure that you understand the difference between a population and a sample. Again, we've used primarily samples up until this point, and this is what we use to describe or use descriptive statistics for. Whereas now we're primarily concerned with population level data in which we use inferences, and that's what we use today with our different types of probability samples, whether it was simple random sampling, systematic random sampling, stratified random sampling, or cluster sampling. Make sure that you can understand the difference between each of these and how we would use that as a social scientist. Coming back up here to a few of these other bullet points that I kind of jumped over is how we can randomly sample and use probability. We went over how we can do that simply through things like cards or six-faced dice, but we can also use that to understand social phenomenon as well. And then lastly, with this idea of the central limit theorem, the big takeaway there is if we sample well enough and have large enough sample sizes, eventually we will get to a distribution that resembles a bell-shaped curve or that normal distribution. And so just keep that in mind. If you have any difficulty with any of these topics, go back and watch those videos. Make sure that you understand them because these are topics that will keep recurring throughout the duration of the semester and the rest of this class. As always, if you have any questions, feel free to reach out to me, and I will see you in the next video.